Hello everyone. We started in the last class the discussion about computing the gradients of a given image. So we also discussed why gradients are important. We discussed about let's say moving from more representative features of a given image rather than looking at every pixel in the image. And we have also seen with the help of some images that in fact it is the edges that carry a lot of information about the content of the given image. To make any inference or understanding and analysis, it is the edges that in fact carry a lot of information. So that's why to compute the edges, we notice that at the edges you could expect a transition in intensities, sudden transition, or in some cases it could be like a ramp like transition in intensities at the edges. So that is where you could use in fact derivatives. So derivative in 1D, when it generalizes, it turns out to be the gradient, which is a vector of derivatives in, let's say if it is a 2D image, in x and y. So that is where we discussed in the last class. That's what we discussed in the last class. And we have also seen the interpretation for computing, let's say the gradient is something which is perpendicular to the edge. Example being, take this is a vertical edge. If this is your direction of, so for this class at least we will consider this is our x and this is our y direction. Okay, so if you consider it that way, you can notice that as you move on in this direction, you have the intensity varying, and there is in fact a set that's what you consider as. So and if you are moving vertically, you could see it has the same intensity. So for all the pixels in this nature of image, it has dou f by dou x element. So this being x and this being y, then your vector is in this direction, right? So you could see now for a vertical, so this gradient is perpendicular to the edge. Of course, you could make a, this is a simplified version where we considered intensity variations along the horizontal axis. And this is another a simplified case where the intensity variations are along the vertical axis. But nevertheless, you could combine both and still you could find out that this the gradient that you compute will be perpendicular to the edge. And given this dou f by dou x and dou y by dou f by dou y, we figure out how to compute the gradient direction as well as the magnitude. That's where we stopped in the last class. Any questions before we go on and looking at how to compute this dou f by dou x and dou f by dou y? That's what we will. So what we figured out so far is, let's say if I want to compute the gradient, let's consider a 2D image, okay? And for the time being, this again notations, we different contexts and different books would follow different thing. For the time being, let's consider that's our x and y direction. So we told that this gradient will be equal to, say, since f is a, this is a image is a, yeah, I'm writing it for the time being as continuous, it doesn't really matter. You could have written the discretized version, something like this as well. Just for the sake of convenience, I'm writing it as f of xy. Okay, then gradient would be dou f by dou x and dou f by dou y. Now we need to figure out how do you write dou f by dou x given x. So x some, yeah, for the time you consider this notation, let's say f of x comma y for this class. So how do you write dou f by dou x? So essentially, for a you make this change, you in the x you make an incremental change, and for those two, and consider two values which are infinitesimally small variation in x, and you consider f values for both and subtract them. Okay, that will be your numerator, and dou x variation will be in the denominator. So now you can you tell me what would be the case if I am considering a discrete values for x? Okay, assume that this x comma y can take only integer values.
The current pixel minus one, the next, and the previous. We can take any.
Okay, so current pixel, well, and the next one. Okay, so what you are saying is x minus of x plus 1. That's what you are saying, right? So
Yeah.
then you need to take here f value of this function at this, which is f of x, minus value of this function at x plus 1, which is equivalent to x plus 1, something like this you are saying, right?
Yes, sir.
Right, good. So just that I skipped there the y parameter that I will keep. And again, what is the denominator value here then? X minus of x plus 1, right? So what I will do is I will take that negative sign into account in the numerator, so that I would write x plus 1 comma y minus f of x comma y divided by 1. Okay, this is dou f by dou x. This f, if I have to be more precise, should write as f of xy. Since I want the derivative, partial derivative with respect to x, I changed here only the x. Okay, this is called as, what is the name for this? I'm sure you would have studied in one of your mathematics courses. This is called
First
as,
principle of differentiation.
right, and forward difference. That's what it is referred to. And there is no reason why you should consider. So what you are doing here, for example, this is of the pixel of your interest, this being x is going positive as you move to the right. So this value, whatever the function value is there at this point, you are simply subtracting that value for this point, and that's the gradient value for this x comma y. Notice here there is x here, so that's the value you are keeping in the output image to this location. And of course I could have done the same thing as, for example, you consider value at x minus 1. So now you, instead of, let me erase this part now. Suppose I'm interested in the value here. I could have considered this, for example, index is, let's say, consider it as x here. Okay, this is varying here. So then this would be indexed by x minus 1 here, this column. So I could have considered my dou x. Okay, the change is x minus 1 minus x I could have considered. Then this would be equal to f of x minus 1 comma y minus f of x comma y by x minus 1 minus x, which is nothing but f of x minus 1 comma y minus f of x comma y by minus 1. Okay, well, I could have written it as f of x comma y minus f of x minus 1 comma y. This is what I would use for the computation of value, okay, at x location again. Is that fine? So now what I'm doing, I'm taking this and this, okay, and from here I'm subtracting the value which is there at x minus 1, that is giving me the derivative at location x. This is called as backward difference. I will now call something, I will first tell you the name, that is referred to as central difference based derivative. How do you say? See, basically we are moving from continuous time to discrete time. So dou x can take in fact values of integers only, that you keep it in mind. Now to find out the derivative at a location x, from the name, can you tell me how I am going to compute dou f by dou x?
Sir, f of x plus 1 comma y minus f of x minus 1 comma y.
Very good. And what will be there in the denominator? Anyone else would like to give it a try, and what should be there in the denominator?
2, sir.
Very good.
2.
2,
2.
correct. See, you are taking x plus 1 here. Okay, what is your dou x now? First one is x plus 1 minus of x minus 1, which is equal to 2. So this is equal to 1 by 2 into f of x plus 1 comma y minus 1 by 2 into f of x minus 1 comma y. This is called as central difference scheme, where in order to compute the derivative at a given pixel, you would be considering the pixels which is there before and after, left to it as well as right to it. Okay, anyway, you are interested in the direction, in the x direction, so you are not bothered at this point about the values in the y direction. That's obviously it's dou f by dou x. Of course, you could just by change of variable now. I leave it to you to write dou f by dou. Okay, we can write it. Of course, let me just write the forward difference for dou f of I'm skipping even, I'm dropping this f of xy also writing here. But what is dou f of xy by dou y forward difference scheme, for example? X
f of
comma,
x comma y plus
y
1
minus
very good.
y plus 1
minus f of x comma
f
y.
of x y.
That's it, right? And then let me directly write central difference now. You tell me what's the formula for central difference?
Half into f of x comma y plus 1
Right,
minus f of x minus 1 comma y, f of x comma y minus 1.
very good. That's all divided by 2. Okay, clear so far? And how do you compute the derivatives in the x direction and derivatives in the y direction? That is all you require for computing the gradient here. Okay, of course, extension to three-dimensional image also, if you have it, it is pretty straightforward. Here you have dou f by dou x, dou f by dou y, and dou f by dou z. So similarly, then you would write an expression for x. Suppose if I want dou f by dou z, it would be x y z plus 1 minus f of x y z minus 1 by 2. That's all. Now, the next question to you is, you want to so is there any way we are have been thinking about these spatial filters? Can this be implemented using any spatial filter? Let's take, to begin with, this dou f by dou x equal to f of x plus 1 comma y minus f of x comma y. Is it possible to implement this using a spatial filter? That's the question. If so, what is the filter? You tell me the size and you tell me what are the elements of it, what are the values of that filter. You have to mention the origin. Okay, once you say the origin, then things would become easier here. So let us say this is my origin. I am telling you this. Okay, I have taken just a 1 by 3 1. Now you tell me, okay, this, let me call for the sake of convenience this as index 1, this is as minus 1. Now you tell me at minus 1 what is the value you want me to keep. You again, let me also clarify. Let's start with correlation. That's the easier one to do it. Now you tell me what are the values here. I want a correlation mask here. Okay, I'm going to directly perform correlation with it. Now you tell me what is the mask.
It is 0 minus 1 1
0 minus 1
1.
1. That's all. 0 minus 1 and 1. Okay, is it not same as for the convolution mask? If you are going to convolve with it, will it not be the same or will it change?
Sir, 1 minus 1 0.
1 you want me to keep here, minus 1 here,
Minus
0
1
here.
0.
This is your origin. Very good. That's all. So this is one example where your correlation mask is not same as the convolution mask. The very reason being this mask is not symmetric, right? So from now onwards, when particularly when the mask is not symmetrical, I should also tell you whether it's a correlation mask or a convolution mask. So if I don't tell anything, okay, for the computer vision course, you assume that it's already a correlation mask. Okay, this is, if nothing is by default, you assume that this is a convenience, for sake of convenience. If I don't give you anything in your question, that means by default, if I don't tell you anything, and if I just simply say a mask or a kernel, okay, then you assume that means it's a correlation mask or kernel. This is the notation that we are going to follow here. Okay, hope this is clear so far.
Yes, sir.
Very good. So now let's write the mask. Okay, again for the this computing it in the horizontal direction, dou f by dou x using central difference scheme. Now you central difference scheme. Okay, now let's again consider this as the same thing, and I'm not telling you anything, so you assume it's a correlation mask. Now you tell me what would be the values for the correlation mask for central difference.
-1/2, 0, 1/2.
-1/2, 0, 1/2. That's all. Very good. Now, you yourself have now knew all these things. Now it's very clear. And is correlation mask same as convolution mask here?
We have a negative sign here, so it will
That's
not be.
right. This is not a symmetric mask. You still have a negative sign here. So here also correlation mask is not equivalent to convolution mask. There is a negative sign there. So whatever result you get in one case would be minus of the other case. Of course, in practice, derivative as the edge could be moving from negative value to positive value or positive value to negative value, it is not going to make as such a difference in terms of its magnitude, right? But orientation would be different. That's what it is going to happen. But still, conceptually, these are not the identical. Correlation mask is not identical with convolution mask. But now onwards, when I don't say anything, you are fine with correlation, because why we are by default taking correlation mask is why to actually flip it. There is no reason. You could directly multiply the corresponding elements, okay, and do the stuff, right? So anyways, what would happen is, in the first in the forward difference scheme and all, you usually won't be, whatever is zero, there is no point to mention, because I could have kept here also zeros everywhere, okay. This, in fact, if I am considering it as a complete a rectangular mask, everywhere is zero. So it is common that people would be mentioning it as just like this, -1 0, okay. But again, people would be sometimes, sorry, -1 1, I made it -1, and here you people would be just simply writing that it as in this manner, -1 1, and sometimes they would be ignoring it, but it's a good practice. You make it a practice to show the origin by just putting a rectangle there, because otherwise it won't be clear. For example, this is 1 -1, but you have to keep wherever you want to compute the derivative, that has to come here, okay. That pixel has to overlay with this rectangular box, okay. And once it comes here again, it is okay. Some people would be, again, I would suggest you or strongly recommend you to keep a box here to identify the origin when you are marking it this way. So this is your origin, and at least the mask shape is symmetric, if not the values, right? You have the now 1 2 3, you have two non-zero values, so that way it is symmetric, right?
Excuse me, sir.
Sorry,
Just a small doubt, sir.
yes, please.
Um, Here, okay, we take this mask and we apply correlation to get the central difference scheme, like to implement the difference scheme, we do that.
Right.
So I have an implementation doubt. Like if we do use this kernel, okay, this kernel has the decimal value or a fractional value, but the
Right.
pixels are actually integers.
Right.
So how will we resolve like multiplying with odd numbers, or if we get a decimal value while calculation?
Very good, very good. This is one thing we have to always keep it in mind. Once you are doing the processing on an image, you would of course end up with the moment you are doing any arithmetic operations, particularly some division, it is quite natural you end up with numbers that are not necessarily integers, first thing. Second thing, these values may shoot beyond the range of 0 to 255 also. So it is important that you do all the operations. So it is actually, while you are doing all the processing, during the processing, you would always do the processing in float or double. Now, good that I'm not sure whether good or bad. You don't really realize it when you are in some of these advanced programming languages. It might itself taking it or doing the conversion, but all the operations you should do in double. So the reason being, you would be getting the values which are floating values, not necessarily integers. It is only at the end what you would do is you would convert them, or you do a quantization only as a last step when you are saving it as an image. Unless and until you are say, even while showing the image, just be aware that it does some kind of scaling there to bring the values into the range of 0 to 255 or 0 to 1, you could call it. and then accordingly give the values of the color grayscale values it would give. But only at the end, while storing the image, you do quantization, but the rest of the operations all you will do as floating point values. Is that answering your question?
Yes, sir. So when we quantize these floating point values, there is some pre-built algorithm that automatically brings that floating point value to an integer. So we don't
Uh,
have to worry about how it is rounding off.
no, I think sometimes you have to worry about it. In fact,
Okay.
suppose even if I had dropped this 2, I could have find out the derivative by even this is also good enough to compute, for example, my derivative, except that my derivative got scaled up by a value of then by 2 here. That's all happened. So just you need to see the min and max values, let's say, okay, in your algorithm. Sometimes this in fact would be required, particularly while you are dealing with these gradients and all. Make sure that comes to the range 0 to 255. Okay, so it is not difficult for you to figure out or realize here that your min value, if you are applying this central difference scheme, can be negative also here, is it not? Because when you are computing it, consider the case at this pixel. Let's say I have 100, okay, and then assume that here I have 120, here I have 200, okay. Then what is my output here when I'm applying the central difference scheme? Okay, see in an image, okay. So for example, okay, anyway, I have drawn something here, okay. So for example, here my value is 100, 120, 200. Okay, you need to find out the derivative at this pixel. What is the value there?
-40.
Very good, correct, -40. Because 120, this you are multiplying, you have on one side here 100, 120, 200, right? You are going to use correlate it with 0, 1, -1, of course, multiplied with 1 by 2 here. So that's would give you, for example, this and this is -200, this is 0, right? Plus 120 whole multiplied with 1 by 2. So this is -80 by 2, that's equal to -40. Correct. So I'm sure you all now realized that when you will be asked, your assignment is already uploaded, okay, which already has this gradients. So you would realize here that you in fact have -40 also. So you do a simple normalization. So assume that you just take a look into your image, and let's say your negative value is -100, and let's say, or it could be -100.123, whatever it is, decimals also it can have. Maximum is, let's say, 200 you have. So how do you store it as an image now? So image, I told you all know now, for example, 8-bit is commonly used, which has a range of 0 to 255, correct? So how do you do that now? You have, for example, let me call whatever now you have is f dash. Okay, since we are dealing with derivative, f dash is slightly dangerous notation. So let me use f1, f subscript 1 of xy as what I have right now. So how do you store it as an image now? Can you tell me now? So let me, for again simplicity, let me call this as f min and f max. Okay, this minimum value and maximum value. Now you tell me how you are going to store it as an 8-bit image. You put it in the mathematical terms and tell me the output which I want it in this range of 0 to 255. Let me call it as f of x comma y. Okay, now the original one, this with this, let me call it as f1 of x comma y. Now you, and I am giving you this minimum as f min and f max. Now you tell me the formula for it.
F min.
Very good. And what is it that I should divide the whole thing with?
F max minus F min.
Very good. Now, what is the range that this whole expression would take range? What is the expression range here you would get here?
It should be either from 0 to
0 to?
1.
Very good. Now, I want it from 0 to 255. Then what will you do now?
Multiplied by 255.
That's right. Then what? Okay, this has solved the problem. If it has been, if you are allowed to take non-integer values, I want it to integer. So just all you need to do is each value you round it to the nearest integer. That's all. Okay. Anyway, the maximum will be 255 here. Okay, 1 when it is there. Anyway, there is anything less than 1, when you round it, it would come to 255. That's all. This is how you do it. This is a very important question that you have posed, because this you have to do it while you are storing the images or even displaying the images. You know that, yeah, usually yeah, there will be something like even image showing. If you are using it, again, this command would vary from software to software, but you would always have, you want to show image before even saving it. If you just want to display the image, in that case, usually this itself would be good enough. This multiplication and ranging it to 255 won't be required. So all you need to do is simply this normalization you have to do. Sometimes the image show, this command itself would normalize and show it, but you have to know what exactly it is doing. Otherwise, sometimes the result you would be getting is not what you intended. You might be getting something else. So you should have very good clarity on what's happening when you are using it to either display or save the image. So we have written, let's say, gradient of that image in the x direction. You have written the mask. So for the sake of completeness and maybe some more practice, you now tell me how the mask would look like when we are talking about the central difference. Okay, now the mask would look like this. So again, let's consider this as x. We already considered this as your y direction, and this as your center. Why is center important? Because that will tell you what the value for a given pixel xy you are computing it. It is the center should match with that particular xy. Okay. Now, so this index of this mask would be, now this is -1, 0, 1. Now you tell me the value starting from -1 down. What are the values now here? If you want, you could refer back here what we have written. Yeah, so look at here and now tell me what's the mask here.
-1/2, 0, 1/2.
Right, correct. That's all. That's the central difference scheme, and that's the derivative in the direction of y. Okay, so essentially you see, it's a slight abuse of notation. I'm using still that continuous time function, but that's okay. The message is conveyed, so I'm okay with it to do that slight abuse of notation. Right now, if you want, you already told that if you want the gradient, again, this is a repetition. So how do you compute it? This is equivalent to, so this is how you compute these masks. Use these two masks. Let's say this mask for dou f by dou y, and somewhere we have written this mask for dou f by dou x, right? Then after that, how do you compute the magnitude? What's the value?
Root of dou fx squared plus dou fy squared.
Right, dou f by dou x, you take whole square plus dou f by dou y whole square. Don't keep that on top of dou there. Okay, that's you. I'm sure you all know it. First derivative square. And again, one more important thing I want you to mention is, see, for every pixel, computing squares of these terms and taking particularly the square root is expensive. Okay, this is a, so you would usually approximate it with simply dou f by dou x. Okay, absolute value of it plus dou f by dou y, absolute value of it. That's how you usually means, anyway there is this is anyway you are trying to put usually to see, irrespective of there is a strong edge or not, at every pixel location when you are doing it, it will have some value. At the end, you put a threshold and keep anything above that threshold to be there. You consider anything above that threshold as an edge, anything below that as not an edge. Okay, that's how you do it. So your threshold would vary, but this is how in practice you would be computing it. Instead of computing this, not because this is more accurate, but it is because it is computationally much simpler to compute. Just you take absolute values here and sum them up instead of taking the square of it, sum them and take square root of it. By no means these two are not exactly equal, but you approximate it unless it is very much required to do it in the original way. This is how you would be doing it. Anyway, then how do you compute the angle of this made by this gradient? That is tan inverse of dou f by dou y divided by dou f by dou x. That anyway you use those two masks and do it this way. Okay. Let's again move back to a 1D signal to make further analysis of it and see what is going to happen when you are applying these masks. So assume that my signal is this way. I'm considering a 1D signal there. This is my x. Okay. I'm just looking at dou f by dou x. Sorry, here you can call df by dx also, because I'm just considering the signal is f of x. Okay. Now, this is what profile am I drawing here? What is the profile here? What is f of x here? What does this represent? F of x is nothing but intensities. Okay, you consider this as one row of your given image. That's what we are considering. So these are essentially the intensity profile for a given row. Assume that. Okay. Now you consider this mask now. Okay, for the simplicity, I'm just taking I don't want to even do 3 operations. This is again for illustration of the phenomena. I'm considering it. So let me simply consider 1 minus 1, this being my forward difference scheme I am considering. Okay, so now can you tell me how this dou f df, I can write df by dx here. By the way, when I move to the 2D, I will make it dou f by dou x. For the time being, this is my f of x and df by dx. Can you draw how this plot would look like? Okay, so basically it has 3 regions. Okay, 2 are similar nature and 1 in between is a different nature. Now can you tell me how it would look like? First of all, you take this let me call it as segment 1, segment 2 and segment 3. What is the values of dou f by dou x for this segment? 0. Correct. See, this is just, as I said, you could think of it as something like 0, and maybe this, if you want 200 or 100, why not 100? So let me put something like 100 here, just for the sake of having some numbers there. So this is everywhere 0. Okay, so this I need to subtract. If I want to compute the value here, subtract its value from the next value. So this all would be equal to 0, right? And what about this region? This region, third region, is again everywhere 0, right? So what is going to happen in this region, you tell me?
No,
Or
sir.
do you, yeah, what is the additional information I have to give?
X-axis coordinates.
That's right. Okay, so if I don't give you, all you could tell is you won't be able to tell what is this maximum, but you would get something like this here, is it not? Suppose if I had give you like this is be my 0, okay, this is my 100, then this is equal to 100x. Basically 100x derivative of it be equal to 100. So this would have been 100, but doesn't really, we are not worried about this exact values here. So let me drop that, but you are getting something like this. So let's not worry about what is this magnitude of the stop, but just for the sake of keeping, let me keep it as 200, 100 here, 200 here and 300 here, something like that. Okay, at which value of x is the edge now?
100, sir.
100 and 200.
Yes, there is an edge here and there is an edge here. How do I know now from the gradient whether there is an edge at that point or not? So that is where, when you compare it with its neighboring values, right, you see a sudden jump here, basically, is it not? That sudden jump is you are able to see. So there is a maximum or minimum at that point. Okay, that is what is going to happen there. Now, suppose instead of having the above profile, so basically, we will discuss it in more detail a little later, but it is enough. It will, the first derivative has a maximum or minimum. This you already know from your calculus and other mathematical concepts. You already know it. Now, suppose there is some noise that got added to this image. So instead of me having a profile like this, my new profile that I have got is something like this, because there is some noise that got added up here. Okay, I am getting just a profile like this instead of getting the profile that is there. This is my f of x now. So this is, let me call it as maybe f1 of x. Original one got some noise. Now what? Okay, now what is going to happen if when I am trying to compute to this dou f1 of x by dou x? Can you see a clear jump like this here now?
Smoothing it.
Smooth
Very
is
good.
first.
Excellent. Smoothing. So whenever there is a noise, that's why we initially discussed with the denoising or smoothing. You do the smoothing, okay? Then you would get a profile close to this. Then you apply your gradient. It is because gradient is very sensitive to noise. Don't usually right away apply the gradient. Before applying the gradient, you apply the smoothing operation, okay, and then followed by it you apply the gradient, right? Is that clear? So if you want to do a cross correlation of it, or maybe convolution also, let me write it because I have some conveniences with convolution. Assume that my original image is f. You first convolve it with a Gaussian kernel, and on the result you convolve with, okay, this is Gaussian smoothing kernel, okay, this, let me call it as g1. Then g2 is my gradient kernel for gx, let's say gradient kernel in the x direction. Then you would get a more reliable result, or where you can get rid of such noise that got added up. So this is what we were discussing. Okay, so by the way, if I had considered an edge like this, I have done a like a ramp like edge. If it is a step like edge, right, then what you would get is, in fact, you would be getting, then if you plot it, you would be getting there a peak there, right, in case of your first derivative. Now what we are saying here is, if you have something like this, you first, let's say, apply a Gaussian kernel, then your signal would become something like this. Then followed by that, you take derivative of, instead of taking derivative of f, you take derivative of f convolved with h, or we used it as a convolution operation, which is commutative. So you could have written it as h convolved with f. Both are absolutely fine. Then you would see the profile like this. Okay, this is again same as if there is, so essentially this is the original one we are assuming, right? To get rid of noise, you are applying a Gaussian smoothing, and then you apply it. Suppose my kernel size is k. Okay, some size, let us still, we are in the one dimensional space only for our convenience. So assume that my kernel size is k. Okay, for each pixel I need to do, let's say, k number of multiplications. Let's not worry about the additions, multiplication is more expensive. And I assume that there are n number of pixels. Okay, so by the time I arrive here, how many number of multiplications I have to do? Ignore about, you assume that you have done enough padding to deal with this, with the boundaries also on both sides. Okay, so now tell me, if I have a kernel of size k, okay, and a signal f of size n, to reach to the stage of h convolved with f, how many multiplications should I do?
Sir, n times k.
That's right. As simple as that. This is not a complicated question. Right. Now, to arrive at this answer now, how many? So now what should I do again? This one again with another kernel of size k. That also, let's assume your Gaussian kernel size and derivative size are same. Okay, for simplicity, let's assume that. Because anyway, to make them same size, it's not difficult. Take which is maximum and bring your another kernel to that size by simply padding zeros to your kernel. Okay, both would be of same size then, right? So now you want to do the result, you want to convolve again with this new derivative kernel. Okay, this is again k. Again, ignore about the boundary pixels. Now, how many number of multiplications in total you are doing now?
2 times.
That's all,
N
2 times. You are
cross
just repeating this operation one more time, right? 2 times n multiplied with k is the number of operations that you are doing it. Now, I am giving you an additional information here that the size of the kernel is much, much smaller than your size of your signal, 1D signal, that is the size of f. Can you think of any better way to do this? Don't think of like how you could optimize convolution. Okay, that's not there, but rather using some properties of convolution, and can you bring this number of computations down? That's the question.
We can take the derivative of the filter and then convolve with the image.
Very good, excellent. That is all you have to do. Instead of taking derivative of h convolved with f, you take derivative of h with respect to x and convolve f simply with that. I have told you the size of h is much, much smaller than the size of f. Assume that both h and this derivative operation is just another convolution. So both are size of k, assume. Then this would simply require k square multiplications, right? If your k is 5, 25 multiplications are required to get a new kernel, okay, which is of size again k. You are going to consider, or yes, it's of size again k you would consider, and that's what you would use. So you essentially yeah, so this Gaussian, maybe this is easier to explain you. Look at here, this Gaussian. So this is, what is this? Is it associative property? If you are changing the brackets, I guess, if I am not wrong. So it is the associative property of convolution you would use, where you take first, given this kernel h, you take derivative of this Gaussian, right? So you could see here at the top for this Gaussian, okay, this value would be, there is a constant, the slope is 0. So that is where the derivative of Gaussian at this point would become 0. I'm just trying to give you some sense on why we are getting something like this. Okay, then this is gradually increasing in this region. So till you reach here, it increases, and then as you reach this top plateau here, then that's when it stops, it starts falling down, and then this is further reducing here. So when you are doing the, let's say, the forward derivative, you have negative values. So even from the formula of taking Gaussian and taking derivative, you would figure out that it looks something like this. And now all you need to do is you just convolve with this one. So assume that this you could all stack up if you are going to do some other operation. So you are doing smoothing here, you are doing denoise smoothing, by mean that denoising, you are finding out derivatives. You could put both, stack them up together and come up with just another kernel, and then you try to, then you convolve that you with that your signal, and would give you exactly the same result. Clear so far? I think I'll stop here and we'll continue. I'll just give you the lead on what we would be further discussing. You would see here a maximum, and think, suppose if I want to take what will, so the maximum of your result, okay, the maximum would give you here, maximum of this function or even the minimum of that function will tell you that there is a strong edge there. And what would happen if I take second order derivative, okay, and a continuation of, so can and after that taking second order derivative also, so there is a derivative and after that one more derivative I am doing it. So if I am trying to do Gaussian smoothing, derivative and derivative of that, what would be the my kernel, resulting kernel? And any specialized edge detectors which does both smoothing and the derivative together. These are the things that we would discuss in the next class, and that's where we will stop. Okay, I'll stop here.